Okay.
Take that as you wish.
I'm not sure how to take that, but okay.
I'm doing all right. How are you doing, Dr. Joe?
I am doing fine. Like I
Dr.
said,
Joe, I need
I'm
to
sitting
know-
out on my deck, so I'm doing it pretty good. It's a decent morning. Yes.
Did you hear about the news
About the news. I'm pretty sure there's more than the news going on. What's up?
about Illinois?
That we're staying indoors for another month?
Yes.
Yes.
And the masks.
Oh, yeah, I heard about the masks. I've been wearing a mask when I go to the store anyway, so.
The good thing is that recreational things are going to start opening up, like golf courses and all that.
Yeah, that'll be good. Having the parks open and those kinds of things will help. Just if people actually, people following directions helps with the. The main thing is to keep it out of the healthcare system because we don't want overrunning the healthcare to make sure that people don't necessarily die of the virus as much as everything else. So the chat went off. I'm just trying to see who chatted. Or you live in Georgia and don't worry about that. That's true, Ashlyn.
Yeah, because they started opening up already.
Yeah,
Yeah, we already opened a few things up today.
you got your tattoo scheduled?
Definitely not. But I'm really
You don't want a
excited that I
tattoo
can
in
go
this?
outside.
Yeah, if you go to Georgia, you can get your tattoo now. So, it's all good.
Yeah.
Go
And,
get. Go
I
ahead.
talked to people who work in the hospitals down here, and they're like, we are nowhere near capacity. Doing all this because it's going to overrun the healthcare system. It's not true. So it's been interesting. But yeah.
Well, yeah, Georgia's had it different than certainly some place like New York.
Yeah, they've got hit the worst.
Yeah, they've had it really
I
bad.
think they've got 146,000 positive patients.
Yeah, it's nutty. Yeah, it's not good, but we'll see what happens. We'll figure out who's right about what needs to be done. I'm certain.
Well, yeah, because for Illinois, our biggest problem is Chicago.
Yes.
It's like New York State. All of our cases is in the biggest city that we have.
Right. Here in Decatur, we have a nursing home that has the glut of the cases here.
Oh, really?
Yeah, one of the nursing homes in town has over 30 cases.
Yeah, it jumped from earlier this week, just Macon County things jumped from 30 something up to 90s, or just a big jump in just one day.
Mm-hmm.
And my dad, he's working in some of the care screening people, so he's been seeing some people, which has been interesting. So.
Yeah, I'm sure. Is he keeping himself away from the rest of the family too then, or?
Yeah, for the most part, one day when he saw one person specifically that he was thinking had it, he stayed down in the basement of our house, has been wearing a mask, but that test came back negative, so, which is good, so he hasn't been working. It's more likely he's just taking calls from people because they're trying to keep people in as long as their symptoms aren't severe. So
right.
He hasn't seen too many people, but yeah, he's taken his precautions. So.
Oh, good. Well, I hope he stays safe because it's scary.
Yeah, it is. But thank you.
Yep, you're welcome. Go ahead.
We only have 3 weeks left.
Yeah. Let's see.
Actually, 2 weeks and a week of finals.
2 weeks and a week of finals. Yeah, and your final is just going to be over the stuff that we're talking about now. It'll be a take home. I'll get that assigned sometime during the last week of class, and it'll be due middle of finals week. So.
Oh, it'll be a take home. I was thinking about going in to take it.
No, it'll be a take home.
Go take it. You take it outside. He'll send a piece of paper out for you. You go. You take. The rest of us are going to have a take home.
Yeah. Yeah, I'll even snail mail it so you have a paper copy of it so that you can go sit somewhere and take it.
Can you mail me the F distribution tables too?
I could absolutely mail you the distribution tables if you need it. Anything else going on?
I'm sitting in my dining room looking outside, and it's a not so bad day. I wish it wasn't as cloudy, but
Yeah, it's not too bad here. Let's see if I can get a video up of my view right now. Let's see here. If I can find myself here, and I need to turn my camera around. If I can do that on here. Let's see here. Hide self view. No. Well, my camera's turned the wrong way. Let me see here. Hold on. This will help.
oh,
There we
oh,
go.
there we go.
Can you see the lake?
Oh yeah. I think it's brighter here.
Yeah, it's still kind of gloomy. It was.
What you have.
It was. Yeah, let's see. That's a little bit better. There's my view from my deck. So, not too bad. But I have I bought a new Surface Book like Ashland's, and I had it flipped on a tablet mode, so it was the rear-facing camera was facing into the keyboard, which is why you couldn't see anything.
You should have blamed Ashland for that problem that you just had.
Well, I did. Didn't you hear me? I always blame Ashland for my problems.
It's your fault.
It is.
Out of your one, and it's the one that you have.
Yeah.
So it's your fault.
Yeah, it's the best one.
Yeah.
It's been sunnier here, though.
Dr. Stiggles writes me a note that says it does not look like stats.
Hey, she's not teaching our class.
They said you're not the one teaching. And she stuck her tongue out at me. Oh, anyway. Yeah, so it's not such a bad day out. It's a little warmer than it was earlier. Because I was sitting out for my 9 o'clock class, too. So, but not so bad.
Nice.
Yeah. I've had worse days.
Went back inside.
What?
Not special.
What's that?
Your 10 o'clock class, you went back inside.
My 10 o'clock class, I've only got 2 more topics to talk about, so I just recorded lecture for them, so they didn't get the live version of me.
Man, they're missing out.
Well, I suppose it depends on who you talk to.
I guess so.
All right. Anyway, think we should do some math?
I guess.
I guess. All right. Well, let's do some math then. So, last time we talked about doing bias. So, remember that the bias for an estimator, which we typically use a hat for our estimators, is just the expected value of the estimator minus the parameter that we're trying to estimate. So, let's just look at this example, see if we can figure out what's going on. So, it asks us to figure out what the bias is for using the square of the mean of this uniform distribution as the estimator for, well, the square of the mean. So the square, I should say the square of the sample mean, using it as an estimator for the square of the mean of the distribution. So we know that since it's uniform on 0 theta, we know that the mean of this distribution is going to be theta over 2. Pardon me. So what we want to compute then is the expected value of the sample mean squared, and then minus the square of the mean. So we would have minus the sigma. Why do I keep saying sigma for the stupid theta? Theta squared over 4. I've said that 2 days in a row now.
Yeah, gosh, stupid theta.
Stupid theta, I know. All right, so this is what we want to compute. This will be our bias in that sample mean squared estimator. All right, so let's see if we can figure this out. So I need to do a computation here for this expected value of the sample mean squared. Well, we know that the sample mean, of course, is the sum of your... Now, let's see, can we do it in terms of... Let's see how I can do this. Well, let's write it a different way. Let's write this as the variance of the sample mean plus the expected value of the sample mean quantity squared. A lot of noise going off in the background here for me. I don't know what all that noise is. All right, so this is certainly, we can replace the expected value of a variable squared with the variance of the variable and then the expected value of the variable quantity squared. And we already said that this part, we know that the expected value of the sample mean is certainly the mean of the distribution. So for this part, we can definitely plug in the theta over 2 and square it. And then for the variance of the sample means, remember that's going to be the variance of the distribution divided by the sample size.
Repeat that again. I didn't get that.
Oh, okay. So we know which part, the whole thing?
Yeah, preferably.
Okay, that's fine. All right, so from the line above, we had replaced the expected value of the variable, which in this case the variable is the sample mean squared, with the variance plus expected value quantity squared. And our x is our, going back up here, is our normal, is representing our normal distribution, or uniform distribution. Words are hard today. We're representing our uniform distribution. So the expected value of x bar, of course, the expected value of the sample mean is the same as the expected value of the distribution. So I just replaced the expected value of x bar with theta over 2. And then the first part is just our central limit theorem idea that the variance of the sample means is the variance of the distribution divided by the number in the sample size. So that's where the n is coming from. All right.
Thank you.
Yep, you're welcome. So in this one, they tell us that we have a sample size of 10, right? Okay. So I know my denominator here is going to be 10. I also can notice right away that these two things cancel, right? These two things give us 0. So all I'm interested in here is just this variance piece. We also know that the distribution is uniform from 0 to theta. So its variance is going to be theta squared over 12. If I remember the uniform distribution variance correctly.
That's correct.
Okay. So this is our bias. So I get theta squared over 120 is going to be the bias in this particular one. And so that the question asked us for that constant that was in front of the c, or the c that was in front of the theta squared. So in this particular one, we see that the c value that they're asking for is 1 over 120. Notice that in this particular case, we could have computed the bias for any arbitrary n, right? At this stage right here, the one that I'm putting the box around, I could have left this as an arbitrary n and still got to this point, correct? So for a sample of size n, the bias in our, the bias in our sample mean squared as an estimator of theta, so sometimes you'll see them put a subscript of the estimator as the subscript. And in other books, they will reverse the notation. I have no idea why. Some books you'll see what they're trying to estimate in the parentheses and what they're using to estimate as the subscript. They do it. This, to me, makes more sense because we want the bias in this estimator. So to me, it would make sense to put the estimator in the parentheses. So that's the way I'm going to do it. In this case, this would be theta squared over 12n. And again, the 12 is coming from the fact that we got the 12 in the variance formula for the uniform distribution. Now, the reason why I'm pointing this out is that, remember, for unbiased estimators, we would need a 0 for the bias. So this one certainly is biased, but notice as the sample size gets bigger, the bias gets smaller, because the bigger n gets, the bigger your denominator gets, so the smaller the bias will get. We notice, we notice that as n goes to infinity, the bias goes to 0. Remember, we said that we like unbiased estimators, but sometimes, even if it's biased, it's not that big of a deal. This would be a case where it's not really that big of a deal if you take a large enough sample size. So the larger the sample size gets, the less and less the bias gets. So it's not going to turn out to be that big of a deal, assuming you use a large enough sample size. So this actually has a name. So if the bias in an estimator goes to 0 as n goes to infinity, we say that theta hat is asymptotically unbiased. So again, even if you can get estimators that are biased, but they're asymptotically unbiased, that's not so bad. Because being asymptotically unbiased, you just make sure that you take a large enough sample size to whatever tolerance level you're willing to live with as far as the bias goes. So we've seen some other asymptotically unbiased estimators. Last time we talked about pardon me, that what some books will refer to as the empirical variance, where instead of using the n-1, you use the n. So then as a estimator for the variance, I believe we said that the bias was negative the variance over n. I believe we did that last time. But again, notice that the bias here, as n gets really, really big, the bias goes to 0. So then the empirical variance, or sometimes referred to if you know the entire population, it'd be the population variance. This empirical variance is a biased estimator, but it's asymptotically unbiased. So V.
Cutting out real bad.
I'm cutting out real bad? Sorry. I didn't even get a notice that my internet was unstable. Usually that's what pops up when I'm cutting out. Is it better now?
Yes.
Okay, good. Oops. So this is, again, asymptotically, right this way, is, and asymptotically unbiased estimator for sigma squared. All right. So there's another concept that goes along with this idea, and it's the concept of consistent estimators. So let me do this off to the side before I talk about relative efficiency. So we say that a estimator for sigma good lord, theta, jeez, is consistent if, so this is going to be a weird statement, but we'll talk through it and hopefully it'll make more sense about what the heck we're even talking about. So this is if the probability that the absolute value of theta hat, depending on some n, usually depends on some n, minus theta, the probability that that is greater than epsilon, this approaches 0 for any epsilon greater than 0. Okay. So by the approaches 0 part, we mean that as n is going off to infinity. So again, let's talk through this and see what the heck this even says, because there's a lot of symbols here, a lot of words, and most of the time we don't put those words in this order. So let's talk about what we mean. So this for any epsilon greater than 0. So what we're looking for is when we're doing the absolute value of the estimator minus the population parameter, this is talking about basically how bad is the estimate, right? How far away is the estimate from the theta? Okay. So what we're interested in is this distance having some positive value. The probability that we have some large, well, epsilon typically we think of as a small number, but thinking about that this actually has some measurable distance, the estimate has some measurable distance from the actual population parameter, the probability that we can actually see this measurement. So this epsilon is, okay, the probability that we get a bad estimate. So think about epsilon as some tolerance level. The probability that we get some bad estimate, that probability goes to 0 no matter what tolerance level I pick. So what that means is that the larger your n gets, the probability that your estimate is bad is small. Okay? So this greater than epsilon idea is a measurement for making a bad estimate. So the probability that your estimate is bad gets smaller as n gets bigger. So it's that idea again that using a larger sample size gives you a better estimate. So that's what we mean by a consistent estimator. So, pardon me. When we talk about doing those bias computations are a measurement of how bad your estimate is, right? Because you're doing the expected value of the estimator minus the true value of the population parameter. So that bias is a measurement of how bad the estimate could possibly be. And when we just talked about those asymptotically unbiased estimators, as long as the n gets bigger, if it's asymptotically unbiased, then the bias goes to 0. Well, if the bias goes to 0, then this probability should also be going to 0 at the same time. So it turns out that if theta hat is asymptotically unbiased, then it's also consistent. Now, it may not be the other way around because there are examples of consistent estimators that are not asymptotically unbiased. And the main reason is because some of those estimators have variances that are undefined. When you do the expected value for the variant to try to get the variance values, they end up being undefined. So the reason why this is not an if and only if statement is because there do exist consistent estimators that aren't asymptotically unbiased, mainly because you can't compute the bias because of issues with existence of expected value. Anyway, so that's what we mean by consistent. So the ones that we've seen that are asymptotically unbiased, though, will always be consistent because, again, what we're doing is making a computation of that probability. That probability can't get, that distance can't get very bad very often because the bias tends to tends to 0, so the expected value tends to where you want it to be. we're not going to do a lot with consistent besides the fact that basically the idea is that if it's consistent, the bigger sample size you take, the better your estimate's going to be. I mean, that's really the whole idea behind that.
Isn't that the case with like every estimator?
Not necessarily. If it's, I mean, every estimator that we deal with, it's true, but if you pick a bad estimator, it may not be. So especially depending on if you're looking at new distributions or something where you don't know what the distribution is, then you might be coming up with a way to try to estimate something, and maybe it's not working correctly because you don't have the correct estimate. But yeah, the ones we deal with, it's always true, because the ones we deal with all have those variances that tend to get smaller and smaller the bigger that the sample size gets.
Dr. Joe, can you scroll back over?
Yeah.
Right.
Sure. If I can get the thing to scroll. There?
Yes. Okay. Thank you.
Yep. You're welcome.
So, Dr. Joe, could you explain a little bit more, like, the difference between, like, this statement that we're seeing now versus, like, the asymptotically unbiased? Like, I guess I'm confused since they're, like, the difference between them, since, like, they're both going to 0 as n is bigger.
Sure. So the asymptotically unbiased statement is talking about specifically the bias going to 0. This statement, it's weird because we haven't worked with a lot of examples where this happens. But with your bias, remember that it was the expected value here. This piece, expected value, it's entirely possible that this expected value is undefined. There are distributions where the expected value is infinity. We can't calculate what the expected value is, but we may still want to try to get an estimator for the population parameter. There are certain distributions that have that, depending on what the parameters are. And some of these actually are ones that are used in probability theory. So it's certainly possible that I'm not going to spend a lot of time on it because I don't really care too much about worrying about those particular types of distributions for our purposes. But it's possible where you can't even compute the bias because this expected value doesn't go to 0, doesn't exist. So if you do for example, let's see if I can think of one. So if you do say your PDF is 1 over x squared for x greater than or equal to 1, say that's your PDF. If you try to find the mean of this distribution, you're integrating 1 over x from 1 to infinity, and that improper integral diverges. So that gives you an example of a distribution which mean doesn't exist. So it's possible that I can't even compute this bias. But I could still possibly but I still might want to try to estimate whatever population. This one doesn't have a population parameter that I'm necessarily interested in for this particular distribution. But I still might be trying to use a particular theta hat to estimate theta. And I would like this idea still to happen. So there might be other ways to check this probability statement without using the asymptotically unbiased part. Does that help?
Yeah.
Okay. Everything that we're going to be dealing with is going to be something that we can compute the actual bias and most likely see that it's asymptotically unbiased. The whole point of that was there are instances where this definition is different from the asymptotically unbiased part. And actually, some books will illustrate that particular distinction by calling this weakly consistent, and then removing the asymptotic unbiased statement and calling it just consistent or strongly consistent. So that one actually gives us making sure that the expected values exist, so it's a stronger condition.
Okay.
I don't know if that helped at all, but
No, it did.
okay, good. I'm trying not to go into a whole bunch of details because I don't care all that much about it except that you know what the word means.
Right.
Yeah. Okay. Other questions on that before I go on? Okay. So let's talk about this idea of efficiency. And before I even start with a problem and give a definition, or the idea behind efficient means that if you're picking an estimator, you would like it to be as close as possible to the thing you're estimating, of course. So if you're doing several samples, you would like those samples to be less spread out, if possible. So if you've got a choice between two different estimators to estimate the same quantity, you would like the one that would have less variability so that you have more of a chance for that estimator to be close to the true value that you're trying to estimate. So the idea of efficiency is this relative efficiency idea. So the definition that we'll be interested in is, we say that theta 2 is relatively more efficient than theta 1 if the variance of theta 2 is less than the variance of theta 1. Both with hats. So theta 1 and theta 2 are both estimators for theta. And ordinarily, we want them to be unbiased estimators. So for this, we're going to assume that theta 1 and theta 2 are usually, we don't have to have it, but usually we're going to assume they're unbiased estimators for theta. Oops, unbiased. Our goal, just to let you know what our goal is, we're trying to figure out if there is, in some sense, a best unbiased estimator for theta. So we're going towards an idea of a minimum a minimum variance unbiased estimator. That's where we're headed. We're not going to get there today, but that's where we're headed. We're trying to get this idea of making the variance of your estimator as small as possible. Pardon me. Again, that'll be based on a particular sample size. I mean, obviously, you can make your variances go down by taking your sample size bigger. So when we say we're trying to make the variance as small as possible, we mean for a particular sample size, making the variance as small as possible. All right.
So if we have two samples with different sizes, then we can't compare their efficiency?
Correct. Yeah, the efficiency will be for both the same size. At least for our purposes. I mean, you could... Yeah, I mean, I guess you can compare their efficiencies based on by different sample sizes. But when we're talking about a minimum variance one, we're talking about for the same sample size. All right, so...
Dr. Joe?
Yes.
For the inequality, is that strictly less than, or is it less than or equal to?
When we say more efficient, it's strictly less than. All right, so when we actually do the computation of the relative efficiency, we actually divide. So when this one's asking us of the relative efficiency of theta 2 with respect to theta 1, this one actually wants us to take the variance of theta 2 divided by the variance of theta 1. That's what we're going to do to figure out relative efficiency. And since it says with respect to theta 1, that's how that I know that I'm putting it in the denominator instead. So we can tell by the fraction now whether or not this is which one's going to be more efficient, because if this fraction turns out to be less than 1, then theta 2 will be more efficient. And if it turns out to be greater than 1, then theta 1 will be more efficient. All right, so for this one now, we know that we're given a sample of 25 items, and the distribution's an exponential one. And we are trying to work with two estimators for the mean. Notice the second one here is going to be biased estimator, but we're still going to do the efficiency test the same way. Like I said, we're going to assume in most cases that we have unbiased estimators. It's still possible to do efficiency relative to biased ones as well. So we're just doing the practicing here with the efficiency part. So we know that we're looking at the mean here, or 9/10 of the mean for the second one. So let's see. We know that when we do the variance of theta 2, that's the variance of 0.9 times x bar. The bottom is just the variance of x bar. On top, we can pull the 0.9 out in front. Of course, when we do that, we have to square it. And when we're dealing with sample means, we know that the variance of the sample mean is the variance of the distribution divided by the sample size. Now, I could compute both of those fractions in the top and on the bottom, but I don't need to because they're going to cancel in this case. And we get 0.81. So using 9/10 of the sample mean is more efficient than using the sample mean. Now, of course, you'll have to adjust for the bias at that point, but that's what this says, that the theta 2 is more efficient than the theta 1.
So would we say that efficiency is just 0.81 or 81% or...
Yeah, we would just say its relative efficiency is 0.81. All right, let's see if we can do another one here. All right, so this first one goes more what I was mentioning before, that you're trying to show, pardon me, that both are unbiased, but one of the variances is less than the other. So the first sample statistic that you're using is the sample mean, regular old sample mean, and the second one you're using some increasing sequence of the sample statistic divided by that particular expression, that n times n plus 1 over 2. Well, we certainly know already that our expected value of x bar is certainly mu. That's not a question. We already know that one. So let's do our expected value of y. All right, so as long as n is fixed, as long as n is a fixed sample size, I know that I can pull this constant out in front. So I'll have, I'll go ahead and reciprocate it, and have then the expected value of this x1, 2x2, and so on, nxn. So all I did there was just pull the constant out in front and take the reciprocal. And we know that expected value breaks up nicely over sums, and then each individual constant will pull out. So I can write this as expected value of x1 to expected value of x2, all the way up to n expected value of xn. Now remember that this is a random sample being taken from the same distribution, so each of those expected values are all equal to mu. They're all the same, because the x1, the x2, and so on all have the exact same distribution. So now I can factor out a mu out of that, out of each term, and we're just left with 1 plus 2 plus n. And now, hopefully, we begin to see why they had that crazy expression in the denominator. This is the sum of the first n integers. The formula for the sum of the first n integers is n times n plus 1 over 2. So we get mu. The reason why that thing was in the denominator to begin with was to make it an unbiased estimator. That's why that n times n plus 1 over 2 was in there to begin with. All right, so we've shown that both are unbiased estimators. Now we want to show that the x bar is more efficient than the y. Well, we already know that the variance of x bar is going to be sigma squared over n. They used the sigma squared for us to denote the population variance. So we already know that. So now it's a matter of computing the expected value of, or excuse me, not the expected value, the variance of the y. So do this off to the side over here. So the variance of the y will be, well, I'm going to do the same thing like I did for expected value. That n times n plus 1 over 2 is a constant. I'll pull it out in front. Remember that when we pull constants out in front of the variance, we got to square it. So you end up with a 4 over n squared times n plus 1 squared. And then we'll have variance of the x1 plus 2x2 and xn. Now again, we're dealing with a random sample. So when we're doing a random sample, all the variables are independent, so we can break the variance up over the sums without worrying about anything with covariance. And then in each individual piece, we can pull the constants out in front. But when we pull the constants out in front, we have to square them. So doing all that simplifying, the first one will just be a sigma squared. The second one will be a 4 sigma squared, and so on down until we get an n squared sigma squared. Right, so this again I did 2 steps at once. Use the fact that they're independent to break the variance up over the sum, and then pulled the constants out in front of each individual variance, and then but squaring them as I did that. So we can pop the sigma squared out in front, and we're left with 1 plus 4 plus 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 n squared. Or said better, this is 1 squared plus 2 squared plus 3 squared and so on up to n squared. So this is the sum of the squares of the first n integers, and as luck would have it, we have a formula for that too. That's going to be n times n plus 1 times 2n plus 1 all over 6. So if we simplify this a bit, we get what? We get 2 sigma squared times 2n plus 1 over 3. If I did my computations correctly.
Didn't you have an n and an n?
Oh, yeah, I still have an n and n plus 1. Thank you. So, no, I did not do my computations correctly. Thank you. All right, so now we need to compare. It's asking us to show that the variance of x bar is less than the variance of the y. So we need to look at this sigma squared over n versus this 2 sigma squared times 3n plus 1, sorry, 2n plus 1 over the 3n times n plus 1. Well, I notice right away that both of them have an n in the denominator. So really, I just need to compare fractions here. They both have an n in the denominator, so that's the same on both sides. But if I look at this one, this looks like the other piece of it looks like 4n plus 2 over 3n plus 1, ignoring the n's and ignoring the sigma squareds, right? This part and this part match. So really I just need to compare the rest of it to a 1 out in front over here. Well, if I look at 4n plus 2 over 3n plus 1, that's certainly bigger than 1 for any n that I have. You're multiplying the n on top by 4 and the one on bottom by 3. The limit, in fact, as n goes to infinity, is 4/3 here, right? It's not even 1. So this is certainly the 4n plus 2 over the 3n plus... that's 3n plus 3, sorry. The 4n plus 2 is, over the 3n plus 3 is certainly going to be greater than 1 as long as... Well, it's greater than equal to 1 as long as n's bigger than 1. But it's certainly the limit as n goes to infinity is 4/3. So it's certainly going to be bigger than 1 eventually, without any doubt. So that tells us that the variance for the x bar is definitely less than the variance for the y. I'm not sure why anybody would ever use the y to estimate the mean, but it gives you an estimator. It's asymptotically unbiased. This piece the variance here will definitely go to 0. So it's, well, certainly it's not even asymptotically unbiased. It's unbiased. It's an unbiased estimator. It's an unbiased estimator. It's certainly a consistent estimator without any issues. It's just not as efficient as using the sample mean, which is not a huge surprise.
And it's ugly.
Oh, yeah, it's not very pretty. I would agree with that. Aesthetically, it's not very pleasing.
Math equations have feelings too.
Any questions on that one?
Dr. Joe, I had a question on the one before it, real quick.
Okay.
So, even though it said it's from an exponential distribution, because they cancel each other out, it doesn't matter?
That one, yeah, it did not matter.
Okay. So, it could have been any distribution?
It could have been any distribution at this point. Yeah, there was nothing special here about exponential or 25, for that matter. All right. Well, we'll do a couple more examples of this stuff next time, making sure we understand the idea of efficiency. So I've got a few more examples in this file. And then I'll also start talking about this idea of minimum variance unbiased estimators and how we get to knowing whether or not we have one. So we'll talk about that next time. Unless there's any other questions, I will say goodbye and have a good weekend.
There's other questions.
There's other questions?